Hi, everybody. I'm Summer Ash. I am a freelance science communicator in my free time, which who knows what that means these days anymore. But I've also been a rocket scientist and an astrophysicist, and I like to talk about all things space, which is why I love participating in these programs. So today we're going to talk about asteroids, and we have two amazing special guests. Solveig Irvine is from Marshall Space Flight Center. She's the mission manager for the Planetary Missions Program Office. And she's responsible for Osiris-Rex mission, which is mainly our focus today, but also the Near Earth Object Surveillance mission, which sounds a little ominous, but also something really good for Earth, I think. And I'm going to get her to tell us a little bit more about her varied background because it's kind of very interesting. Also, we are joined by Dr. Christopher Steen. He is one of the top experts in Astro Materials sample preparation, which is key because Osiris-Rex is getting a sample and we need to prepare it, protect it, all those good things. And he's also been involved with several other space missions, including Stardust, which was an earlier sample mission return, which is just amazing that we can even do that. So I just wanted to start for people that don't know Osiris-Rex very well. Solveig, can you give us just like sort of an overview of this mission?
Sure thing. So we launched Osiris-Rex 4 years ago on last Tuesday, the 8th. And very exciting. And we, arrived at Bennu, which is an asteroid that we've chosen. I'm sorry, I'm getting tons of feedback. I'm going to turn my volume down. But yeah, so we basically chose Bennu, which is this awesome asteroid, out a little bit away from Earth, because it has composition that we think could lead us to how life on Earth started. It has the potential to have like water-containing clays and some other carbonaceous materials. So that was why Bennu was selected. So Osiris-Rex basically flew out to Bennu, and it's been circling it and taking images and getting ready to actually impact the asteroid and take a sample and bring it back to Earth. And its main focus is to, get a really nice, pristine sample of this asteroid to bring back so we can study it, which is where we hand it off to Christopher, and he's going to do all sorts of really cool things with it.
How is like one out of the whole asteroid belt chosen as like the target? I mean, is there like a down selection?
To get to Bennu? Yeah, so there's, lots of different, thousands of different asteroids and different materials, and Christopher could probably talk more about the details of this, but through different imaging we've been able to do through satellites and telescopes, here on Earth and out in space, we selected Bennu because it looked like its regolith material had composition similar to what we thought Earth, it may help hold keys to how Earth started, right? And so Bennu was selected for those types of reasons. And it's a really kind of cool asteroid and one that we didn't know much about before Osiris-Rex went out there.
And so you said it got there like in the end of 2018, right?
Correct, yes.
And then since then, it's just kind of been reconnaissance, up close reconnaissance?
A little of both. It depends on your term of up close, right? Yeah. So we've been in an orbit, out a couple miles from the surface of Bennu, and we've rotated around to different orbits, so kind of around this way or up and around this way, right? And when we got to Bennu, we found, we were expecting it to have more sand-like composition. And when we got there, we found that it was covered with these giant boulders and really cool rock formations and, just different than how we expected. And so we had to kind of figure out where are we going to take our sample. So we looked for varying topography type sites, craters that look like they would have good sample locations and things of that nature. And so we ended up selecting 4 candidate sites, and we did some, surveillance observations around those. And then in December of 2019, we down selected to our primary site, which is Nightingale. And so we have a backup site, Osprey. So if Nightingale had problems, we had a backup site. Everyone likes backups. It's good practice. Yeah. And yeah. So, so then we did lower and lower orbits towards these reconnaissance missions. So we took images from a higher altitude, from a medium altitude, and then from a lower altitude in order to get, finite detail of these different locations.
And Doss, isn't there a picture I think that we have that shows like a parking lot graphic in the middle of the
I have like 100 pictures.
Yes. So I can show you all of them. So if you want to go to the 4 sample sites, there's all 4 sample sites from 2019. I have a cheat sheet of all the things I sent you. But that will have the 4 different sites of the Nightingale options that we went to. Yep. So you can kind of see how these all have a little bit different topography to them. The craters are a little bit different. There's rock formations. Some look more fine than rocky or bouldery. And so from these sites, Nightingale, which is on the far edge, is our primary site, and Osprey, which is in the, I guess, 3rd or 2nd, depending on which way you go, that's our backup site.
And why all the bird names?
So there is a history of that. So Bennu was actually named by a 5th grader. I think I have my information right. I'm going with my memory. I apologize if I'm off. It was a contest, and it was a 5th grader. And it has something to do with birds and it's a historical thing. I know, Christopher, do you know more of the details? I've read it a while ago, but it's really cool. So everything with Bennu has to deal with birds because of how it was named and its history. So everything is bird names. And
I think it's
yeah, go ahead.
It's related to an Egyptian mythological bird.
That's it. Yes, thank you. Yep.
I like these themes. Like one of my favorite facts is like on Mercury, all the craters are named after like poets and writers, which is kind of cool.
It's very cool.
Yeah. Okay, so this is a sample return mission, which sounds futuristic that we can do this. But Christopher, we've done this before, sort of. What was the Stardust mission collecting?
So the Stardust mission was targeting comet dust, collecting comet dust from Comet 81P Vil2. And it didn't actually land or touch the surface. It basically flew through the tail of the comet, and it embedded particles of the comet in this exotic material called aerogel, which I think I have a piece of right here. I'll show you here. Cool. You can see that there. It's this really bizarre exotic material, and it's only a few times denser than air. And the idea is that the particles, which are traveling relative to the collector at 6 kilometers a second, would slow down enough that we can preserve them intact, which we did, and then bring them back to Earth and analyze them. And so that's been happening for the past, 15 years now.
That's how old that mission is? Oh my gosh.
Yeah, it returned in 2006. It launched in 1999 and it returned in 2006. So it was the first sample return mission of its kind, but it returned very little mass because we were flying through and catching dust. So the holy grail is to be able to touch a surface and collect something very passively and bring it back, which is what these new missions, Osiris-Rex, and then also the Japanese Space Agency's Hayabusa 2 are doing.
And for comparison, how is Hayabusa or is Osiris-Rex using a similar physical mechanism to do the sample collection that Hayabusa
They were
2
very
had?
different. They were very different mechanisms. The Hayabusa spacecraft would fire a projectile into the surface and eject material back into a very small collector. Osiris-Rex has a much larger collector called a TAGSAM, and it will touch the surface and then fire jets of nitrogen gas to dredge up material into this larger collector, and it could collect up to 1 kilogram of material versus about 100 milligrams for Hayabusa 2.
Oh, so a lot more.
Yep.
Yes.
And we do have, sorry to interrupt, Christopher, we did pull there's a tag sample head simulation.
Oh, excellent.
If you want to show, because it shows how we collect it.
I noticed when I was looking at the files that there's, I like the abbreviations, like the SAMCAM. Is that like the sample camera? Or sort of?
Yeah, like a lot of those have those kind of names. Yeah, it makes it easier.
Totally.
Which video was that? So the sample collection. Which one did you want there?
It's actually like a GIF, I guess, but it's a tag sample head simulation. It
Okay.
has it looks like a
Aha, got
kind of
it.
like the head there. You can see it's got little dots. That's it.
There you go.
Oh,
Sorry
yeah,
about
there
that.
you go.
No,
Oh,
you're good. So I don't know, Christopher, you want to talk about this or how it comes down
Right.
and
So
impacts?
basically, it's touching. It's on this pogo stick sort of mechanism, and it touches and it ejects this nitrogen and dredges material up into these side collectors. In addition to this main mechanism, there are also sort of sticky contact pads surrounding the TAGSAM collector, so it will trap small particles of surface regolith and bring those back.
Yeah, you can kind of see them in the simulation before it cuts away, and then they're also on the bottom as well.
Right.
And if you want, also there's the sample arm deployment, and that shows kind of how the arm comes down. It's almost like you're saying, a pogo. See, that's Osiris-Rex there, and you can see how the arm comes out, and then the TAGSAM, the sample head, is there at the bottom, and how it kind of articulates like a wrist.
yeah, I feel like I've heard everybody refer to the mission as going to like fist bump the asteroid.
Yeah, pretty much.
Yeah. It's a very challenging thing to actually land on such a small body. I don't know if you remember Rosetta and the Philae lander. These are complicated maneuvers, so it's great if you could just go and touch down and then bounce back up with material.
Yeah. I think I read that this is like the smallest object ever to be orbited.
Yeah, it's only about 500 meters in diameter.
Like half kilometer. So it's really, oh, someone had a cool graphic that showed.
There's a Bennu size compare you can pull up.
That one.
That I thought was really cool.
Basically just emphasized that it would destroy Manhattan to me. But yeah.
It didn't burn up on impact, yeah, you know.
Yeah. Yeah, it just, that makes it seem super small, even though I know to some people that probably makes it seem ginormous, but it seems tiny. And all these pictures just make it look like so rocky. Is it really rockier than was thought?
It really is. I mean, if you pull up there's one that's Bennu from 4 miles away from the checkpoint. That one we took, so as he said, we do our tag sample, right? It's like that fist bump we do. Well, we're navigating by a thing called natural feature tracking. All the images that we have mapped of the surface of Bennu, all of our sample sites down to the tiny little rocks and pebbles and everything else. And we know exactly where those are. And so does the spacecraft. And so the spacecraft uses that in order to navigate where it needs to impact to fist bump, right? And so this image was taken, we did two practice runs of that, right? And then the final tag will be in October. And the first practice run we called Checkpoint. We went down about 65 meters above the surface or so. And this image of Bennu was taken as we were about 4 miles away after that checkpoint, as we were entering back into orbit around the asteroid. And I mean, you can kind of see it's not a smooth surface at all. I mean, you can see some of these giant formations. And that was one of the challenges about how do we, sample on this asteroid. And if you go to there's one. He's 125 meters across.
Okay.
But there's a lot of rocks, and sometimes my memory's not the best, but I mean, you can just see the detail there that we're able to pull from this, as well as just the size of that rock, right?
Yeah.
If you go to the Nightingale selection size graphic that I sent, so just to give you an idea, that orange circle is the perimeter we originally thought we would have in order to take our sample, right? What we end up having is that blue circle, which is way down there. And you can kind of see, this is like an overhead image of what it would look like with a parking lot with all those rocks around it. And so if you go to, I believe it's the OREX landing overhead, hopefully I labeled that one right. This one kind of illustrates that parking lot. If I sent the right one, this would illustrate that parking lot from above. So you kind of watch, and then we're going to get closer, and you see that's the original landing site we thought we had. And then that's, our original tag zone, and that's our new tag zone. So it's 26 feet. and then there's these rocks that are kind of like cars, and we have to come down within the center of that circle and do our fist bump there. And if you go to the tags, I'm sorry, which one is it? The parking lot side view, that actually is a graphic that the team made that kind of shows it from the side. And it's a really cool to kind of illustrate it. So you can kind of see here in a 3D graphic, those cars, and then how big those rocks are around it, and how we have to come down in there and touch.
Yeah, and that's nice scale, because so I guess the spacecraft is roughly bigger than a car, but roughly that kind of size too.
I believe it's like 8 meters by 10 meters by 20.
Okay. It's a bit
So
boxier.
big, but it's
Hold a car.
boxy. Yeah.
Yeah.
And if I had those wrong, Chris, please correct me.
I think that's about right.
Yep. It's been a while. I've looked at those. So if you go to the natural feature tracking description, that kind of highlights how I was talking about that. And that's kind of a hard thing if you can zoom in. Yep. So what happens is the spacecraft comes down, and you can see if those red zones are the big rocks, like we were just looking at that parking lot image. So that center is where we want to be. And so if the spacecraft is coming down and it's telling it, hey, you're good, you're not going to hit anything, it's going to come down and it's going to tag. And the spacecraft is smart enough that if we're off center a little bit and we're coming down and it says, I think you're going to hit a car or a car-shaped rock, that the spacecraft is going to automatically go back to orbit and it's going to reset. So that way the spacecraft is protected, and it's a really neat system and how they've done that. And as you can see, the imagery is phenomenal of all these different, surface formations and things. When you think about this is an asteroid in space, rocks in space, it's phenomenal.
Do you have a limit of how many times you could potentially abort and reset?
Yes. There's a couple limits. There's the system limits, because there's only so many times we can do that because we have so many nitrogen bottles and fuel and things. Right. But there's also a timeline with it because of the fact that the asteroid is in rotation around the sun. We're eventually going to hit thermal windows where it's going to be too hot for us to get a sample. And so we have a longish period of time. We have till, I think, next year sometime to make sure we get this. But we do have to be in proper orbit. There are some steps we have to take with the spacecraft, because, you can't, it's not like a joystick that you just drive, right? It's not like your video games. Our team has these phenomenal programmers, and I mean, everybody on the OREX team is just amazing. I'm constantly impressed with just their professionalism and their abilities to do things, even in the pandemic. And so, they make these commands and they send them up through the deep space network, and then they have to go to the spacecraft, and then the spacecraft have to execute them and then send feedback back through the deep space network. So it's not an instantaneous type process either.
What's the delay time between here and the asteroid?
It depends on what's being done and things. I think it's anywhere from a couple hours to a couple days.
Okay. Wow. Christopher, are you involved with the mechanics of designing the sample collection? Or does the majority of your work start once we get it?
The majority of my work starts once we get it, although a lot of the work is preparing for when we get the sample. The TAGSAM head was designed and already deployed before I started working at Johnson Space Center. So that was mostly the work of Lockheed Martin with scientists and collaborators. But my job is all about what happens when it gets back.
And are you the person that gets it and holds it first?
So no, I don't know if there will be one person who gets it and holds it first. It's going to land in the Utah test range.
Right.
Right. And it has to be recovered. And then it's going to be placed in a nitrogen purge in a temporary clean room there, and then transported back to Johnson Space Center to Building 31, where we have a new lab specifically constructed for this. And then at that point in time, the curator, Dr. Kevin Reiter, who is a curator for the meteorite collection and also for Osiris-Rex, will begin kind of coming up with a plan for photo documentation and what we have. Lockheed actually will deliver it and open it. And then once it confirms that they have samples, they'll transfer that over to NASA.
Yeah, I forgot. That makes total sense that you would want to like photograph everything so you knew exactly.
Oh, documentation is extremely important. Yeah.
Yeah. It's for heaven forbid you need to back out anything. What happened to it?
Yeah.
Is it going to get split too then between a bunch of labs or agencies at all?
So we have an agreement with the Japanese Space Agency, JAXA, where they are going to share 10% of their Hayabusa 2 sample with us, and we're going to share 3% of our sample with JAXA. And so that way both agencies get sort of a bit of sample. But we've had this long-standing relationship with JAXA, actually. We have asteroid particles from their first Hayabusa 1 asteroid sample return mission.
Did that one also grab a sample, or was it from the surrounding space just above the surface?
It had a similar sampling mechanism to Hayabusa 2.
Okay.
It didn't work as well as they would have wanted it to. It kind of didn't work very well at all, but they were actually able to recover the sample, bring it back, and there were asteroid particles in there. So it was the first asteroid sample collection. This one, Hayabusa 2, went much better, and they may get quite a bit of material back in terms of what they expected. So there's that exchange. And then I think also the Canadian Space Agency will get some sample as well.
I remember you saying something about like there's like maybe a space material sample vault where material goes will never be touched.
So the Astro Materials Curation facility, which is in Johnson Space Center, it curates, I mean, its most famous collection is the collection of lunar rocks brought back from Apollo 11 through 15. And there's also a meteorite collection. We go down to Antarctica and collect a number of meteorites every year. There's a cosmic dust collection where we fly high altitude aircraft to collect dust from comets and asteroids from the stratosphere. There is the Stardust collection, and then there's the Hayabusa 1 collection. In addition to also space exposed hardware. Anytime we get spacecrafts back and have micrometeorite impacts, we also curate those there. So we have a number of those collections, and for all of those, there's a certain portion of that, maybe like 20% or something, that is stored in sort of an off-site location in Nevada, I believe.
Yeah, I'm sure you can't tell us exactly where.
Yeah, I actually don't know where it is. I've never been. Other people in the agency have, but I have never been to that facility.
Is there anything at Johnson with a public display of any of those kind of samples? I mean, I know we've all probably seen like a moon rock at a museum somewhere, but some of that other stuff sounds really cool too.
I do think that they have moon rocks on display at Space Center Houston, which is sort of the museum portion of Johnson Space Center. So they have some there. They might have actual touch samples. And we do a lot of outreach events also, where we'll go and bring samples for people to see. The last one I did was at the Comic-Con here in Houston, which was kind of cool.
I want to see the flight hardware, because we did an earlier one of these with Mike Massimino, and he mentioned like when he first saw Hubble up close, how dinged up it was, which just
they're just all sorts of micrometeorite impacts. And you know, a lot of people want to study the orbital debris hazard for astronauts and future activities in space. Yeah,
very true. Solveig, you mentioned the idea of so much having to happen during the pandemic. What all has had to happen? You only joined right before the pandemic, right?
Correct, yeah. So I joined in December, and then pandemic happened in March. And, you know, we were supposed to have our checkpoint in April, right at the end of checkpoint, or in late March, right when COVID hit, I'm sorry. And so because, you know, that had to be done in the facility at Lockheed and lots of safe things to put all the measures in place, we pushed it out a few weeks so that the people had time to get everything done. And I mean, the team's amazing. I mean, they had to go in and socially distance. So we had to move some computers and, run cords places and get it all going. And, they just did an astounding job with all of that. And, so I stayed, in Huntsville where I'm from. And so I ended up tying in via WebEx to, talk to them and hear things. And we all cheered together and and the same thing. So we had the checkpoint, which was our first practice run where we went 65 meters. And then we had match point where we went 40 meters above the surface. And that was in August. And all of these things were done in the middle of this pandemic, where people are taking temperatures before they come in and wearing masks. And, so it's been a bit strenuous and making sure that, because I mean, some of the locations where the Deep Space Network have also been hit hard by COVID. So they were running on skeleton crews as well. And so it was always very kind of just an unsure environment. But, our team they were just amazing. They pulled together and did it. And TAG is also more than likely going to be in a pandemic. It's October 20th. And so we're all going to be remote. So I'm going to be tied in from, my office in Huntsville and cheering when I see everything. And but it's a whole new way of looking at things, because you can't just go and talk to people, and you have to practice how your communication goes, because you can't just sit in a room and be like, hey, did you see that? Maybe we should change it. You have to call them and then make sure you're describing things correctly. And so it's a whole new way for everybody that has to work. And, space is no different. I mean, all of our lives are virtual now. I mean, so it's just been a huge impact on the team. But so it did shift our tag just a little bit. But our checkpoint went great, our match point went great. And I think if you want to see some cool videos, if you go to the Osiris-Rex match point SAMCAM image, and that shows, so this is as we're coming down, right? Our arms extended and our little heads extended. And you can see Nightingale Site coming up at the top there, right? And then it just kind of replays. That's the spacecraft coming down,
right,
and 40 meters above. So the accuracy of that, if we had continued on, we would have hit dead center in that blue circle.
Wow.
Which is just highly impressive.
Yeah. You mentioned Lockheed. Is that where like your mission control is?
Yes. So the mission support area is at Lockheed. And a lot of our programmers and our team is at Lockheed. So Osiris-Rex is a partnership between University of Arizona and Lockheed Martin and Goddard, Marshall, headquarters, of course, is involved, Johnson. So, we have just so many people involved in this from all across the country. Yeah. And, so to get them all together and be able to do this. But yeah, most of the hands-on work is done out at Lockheed.
So amazing.
Isn't that cool? It's just so cool. And there's another really cool one, if I can just bug it here. If you go to the checkpoint nav cam, if we're not running out of time.
No, we're fine on time.
We have lots of time.
Oh, perfect. All right, good then. Yeah, the checkpoint nav cam actually shows kind of like an image of Bennu, and then you'll see we like slew off into space. So you can see Bennu's coming there, right? There's Bennu coming up. And you can kind of see the different craters and things. And then we're going to like slew off into space a bit, and it gets dark. And then it's going to come up, and you're going to see Nightingale right there at the bottom of the image as soon as we get there.
Oh, yeah.
There it is coming in. So it's just a different perspective of the asteroid as it, you can kind of see it coming in, and then you kind of we slewed away a bit, and then we came back towards it, and you can see Nightingale there. I think there's just, over 1,000 craters on Bennu. It's an amazing surface. And you can see just, how crazy the topography is and stuff. And so that's our sample site right there.
Yeah.
And this was taken in April at the checkpoint.
So Christopher, you showed the aerogel, and then we've seen the image of how this particular sample is going to get recovered.
Right.
In the lab, then, is that going to be much easier to just sort of pool the sample than it was to try and like pull things out of the aerogel?
There are going to be different challenges with the sample.
Oh, yeah. So
it certainly will be easier. I think a lot of the focus when this returns will be on sort of the larger chips. I predict there's going to be, large chips and things like that. And then there's also going to be a lot of dust and fine grained material. And I think there's going to be a lot of focus on those large inclusions and chips and things like that initially. And so I don't anticipate that's going to be anywhere near as challenging as getting particles out of aerogel. But there will be other challenges. So for instance, the contact pads, which are this Velcro-like material that will trap particles on the surface, those are going to be very interesting for people who want to know what the space environment, the space weathering effects are going to be on that surface. And so the goal will be to carefully remove those particles, some of which will be in the 100 micron range, and remove them and store them in a way so that we maintain the orientation so we know what side was seeing space. Yeah, so this picture is actually this is a picture I like to show because at the 100 micron scale, gravity is not such an important factor for particles. The electrostatic forces and the intermolecular forces like van der Waals forces sort of dominate the behavior of these particles. And it's very similar to how geckos adhere to surfaces. So there are a lot of challenges just handling these particles and removing them from a collector and then placing them on some kind of analytical substrate. And the biggest challenge, of course, is when you're trying to move a particle, you might lose it. I think there's actually a video of that where there's a particle transfer loss video that shows sort of the nightmare of the curator, if you can find that one. Is that
I think there we go. That's it, isn't it?
Yes, I think that is it, yes. So this is probably a 20 micron particle being removed from some storage wells on a germanium wafer. And you can see the particles dancing around on the tip of that needle.
Yeah.
And it's charging up and there it is,
Whoops.
it's gone. That's just sort of the nightmare. That's sort of the nightmare scenario for those kinds of transfers. And hopefully with Osiris-Rex, we're going to get a lot of samples, but you know, there might be one important inclusion that can completely change or confirm or validate hypotheses about the formation of the solar system, and you want to make sure you get it into your instrument and do everything right. So a lot of my job has been understanding this problem of how to manipulate small micron to 20 micron sized particles.
How did you get into Astro Materials?
You know, I kind of sort of fell into it. It's funny. It's because it's kind of like falling into the right place. I've always loved space and I've always loved rocks. So this is just like a perfect place for me. But I was working at a lab as an undergraduate at UC Berkeley. And I was working for an experimental astrophysicist who had a completely different project involving cosmic rays. But he was kind of interested in this problem of how to get particles out of aerogel. And so he thought that would be like a fun and interesting undergraduate project for me. And it sort of ended up after I graduated. I continued to work at that lab, and it ended up with us installing an apparatus in Johnson Space Center to do these extractions, and that's being used today. So, and then after that, I was like, hey, I should study these things for grad school. So I went to grad school and continued that work.
Yeah, it's cool. It's kind of like a confluence of a bunch of fields, like astrophysics and material science, but engineering as well. And clearly physics.
Yeah, you know, I really think that Astro Materials curation is something that a lot of people don't know about. But it's a really fascinating convergence of science and engineering and kind of almost a little bit of art, you know, in terms of technique development and sort of creative ways of thinking about samples. So it's something for people who have a hard time focusing on one thing, like me.
Yeah, I didn't know about Astro Materials until I met you. So that was very cool to learn about. And you're right. Like, I feel like not enough people realize how much creativity, science, and anything but technical, but like a mission like this, all of the creativity that has to go into figuring out how it's going to be designed, how you're going to touch down, and then how you're going to extract things.
Yeah, so like Johnson Space Center has, in our Astro Materials curation facility, we we manage collections of things that have been returned, but we also have sort of an R&D, advanced curation division, where we have researchers looking at various aspects of future sample returns. So there's trying to understand how to curate samples and maintain them in a cold environment, cold curation. There's understanding the contamination and alteration of samples due to biological, microbial things in our labs. There is me, I'm working on small particles. There's looking at the toxicology of these samples. Like if you have astronauts and they're constantly exposed to dust from Mars or the moon, how is that going to affect them biologically? So there are a number of things that we're looking at that aren't involved in curating any specific collection, but they're going to be applied to current and future collections.
Right. Is that what you have to wear?
Oh yeah, so most of these labs we're wearing full, we call them bunny suits, and they basically keep our skin cells and lint from our clothing from contaminating samples. And we're usually working in nitrogen purged sample cabinets, or these glove boxes. This one here is located at JAXA, and this is their Hayabusa sample, their glove box. And they have interesting micro manipulation devices that are all materials compliant. You can't have a bunch of different materials working on these samples, because, you know, if you find, oh, here's an interesting inclusion, and you find out it was just a chip from a piece of brass on your material, that you don't want. So we usually restrict things to a very specific kind of aluminum, stainless steel, quartz, Teflon, things like that. We usually have very strict requirements for what can go in a glove box. So that makes it, of course, all the more challenging. You're handling 10, 20 micron particles. You want to keep them from charging up, and you can only use 5 materials. So,
yeah, that almost sounds like the you know, the on-Earth version of planetary protection, where they have to sterilize the spacecraft and everything. So I guess Osiris-Rex probably had to go through something like that too, because it's collecting a sample. So you want to make sure you're not including in the sample something you brought along with you.
Yes, and I think, you know, for depending on where we're going, we have sort of risk assessments for whether or not we will contaminate it, or whether we'll bring something back that might be possibly alive. Hayabusa, Bennu and Ryugu have very low risks for that. If we were to bring back Mars sample return, there is an issue of planetary protection, and that has a whole different process that we're currently going through with Mars 2020.
Yeah.
So.
Or now, if you want to go to the clouds of Venus, it's also an issue.
Yeah, maybe.
Very true.
Maybe.
Yeah.
So like, you also have this interesting path to where you are now. What did you start studying? What did you start out working in?
So I'm a chemical engineer by training. I started working out in aerospace fuels. I did development testing for different applications, mostly hydrocarbon based. I did a stint doing marine fuels as well. So I've kind of done all sorts of interesting things. I've done vehicle design and verification and requirements and things on the SLS vehicle, on several of the upper stage designs for it. And it's just been kind of cool. I've been able to do a lot of different things through a lot of different industries. So it's been kind of a circuitous path to get here as well. But, you know, I mean, my first Cabbage Patch was an astronaut doll, right? So, I mean, space, like Christopher was saying, like, you just grew up like loving space. And so when I finally landed in Huntsville and had the opportunity to work in a space program, especially just an amazingly cool one like OREX, then, you know, I jumped at the chance. But yeah, so I've had a little bit of a different path, but, you know, I've dealt a lot with carbonaceous deposits and different, you know, areas of that. So I'm really excited to see what kind of carbon products we get from Bennu and how it relates to what we've seen here through other things.
Yeah.
I was just noticing in your background, speaking of space, you have a B-wing, and it looks like the back of an Imperial Star Destroyer and an X-wing in the background there.
Yes, yes, we
Slave One
love
too is
Legos
back
and
there.
Star Wars and all sorts of space things. So yeah.
But I also spy the Jack Skellington.
Ah, yes, yes, we're huge Disney fans also. But yeah, it's all fun.
I think it's really cool. And then I mean, I feel like it's important to talk about how you can have such a varied background, and there's not like one true path to any job. I mean, in academia, that's like the big thing, is breaking that stereotype of the one true path to studying your subject and excelling in it. But I think it's really cool when people hear about all the different things that you can do along the way to whatever you're doing now. And so much of it ends up being transferable skills anyway, because
Well, and so many jobs, when you're going through school, you're given these kind of majors to choose from, and you go through school and you learn all these things, and the more you learn, the more experience. But like Christopher's job, I mean, space curation is such a cool thing that you're not necessarily going to be able to find a program on space curation. You probably can now, but for a long time, it was a harder thing to do. So you had to kind of stumble and try. And I think one of the things that's important is, try things, right? So hey, I really enjoy science. I really enjoy chemistry. I'm going to go try this. Oh, I love this part of chemistry. I had friends that went into, organics or inorganics, because you start getting passionate about certain things and you can latch onto that. And then it's like a tree, and it just grows into new opportunities. And like you were saying, all these skills you learn are so different, you can transfer them to different things. And I really think that being open-minded to try any new experience that you have the opportunity to is hands down, especially for I know right now with COVID, but I don't know, you said your undergraduate projects and stuff. I did a lot of internships and co-ops, and that allowed me to try. I've worked in a chemical factory, I've worked at automobile plant, I've developed all sorts of things, and they were all through co-ops and internships that I got to go and try new things for a short period of time. And I don't know, did you have experience that helped me decide what I really liked and what I didn't like? I mean, Christopher, did you have similar experiences, or your undergraduate project?
Yeah, I was going to say, I was going to say that in when I started studying physics in Berkeley, one of the things that people told me was, you could learn physics pretty much anywhere, but the real gem is doing research in labs that are doing cutting edge science that you can participate in as an undergraduate. And that's really, those are the real reasons why you go to universities where they're doing this kind of research, like University of Arizona or UCLA or places like that, where they're hands-on working on missions. It's an exciting opportunity as an undergraduate to do. And then, there are all sorts of other opportunities that might not be what you think you want to do, but I had no idea I'd be doing this 20 years ago, and I've been doing it for 20 years now in some capacity or another. So, it's just like, well, this is what I'm doing now,
Christopher, what are you most looking forward to once the sample comes into your lab?
Seeing what it looks like. I'm really excited. So, asteroids, we have lots of asteroid samples already in the form of meteorites. And, a lot of what we know about the early solar system comes from studying these, but what we don't know is whether we're getting a representative sample of what's out there. We're getting the stuff that's surviving re-entry into the atmosphere and has enough tensile strength to survive the ram pressure. So it could be that we open the sample and we get things that look kind of like meteorites, but then we get things that we hadn't really seen before, like very porous, friable material that we'd never get. And that, to me, seems extremely exciting.
Yeah, that's such a good point.
And maybe
that we have all the samples that we have existing have been contaminated or interfered with by the atmosphere. So things have happened to them, and now these are going to be ones that are pristine.
Yeah,
exactly. So that's going to be very exciting. These two asteroids, Bennu, that Osiris-Rex is going to, and Ryugu, are the first carbonaceous asteroids that we're visiting. Hayabusa 1 went to sort of an asteroid that we think is a parent body of ordinary chondrites. Carbonaceous chondrites are a different kind of meteorite that have a lot more organic material. You see a lot of complex organic inclusions in there. You see very primitive inclusions that we think survived from the beginning of the solar system. You find pre-solar grains. These are things that have condensed in the atmospheres of other stars and survived incorporation into our solar system. You find inclusions that were the first things to condense out of a gas of solar composition. So you're getting this really great sample of really pristine first things in the solar system with these samples. And that's going to be very exciting. And you're going to be able to do it without the conversation of how is this altered on the Earth's surface.
Right. How true is the color in these images? To like the color of, you're talking about, you want to see what it looks like. Is it going to look
I don't know specifically about the color, but I can tell you in terms of contrast, these things are very dark. They have very low albedos. Like if you were to look at these things, they're much darker than asphalt. So when you see these, they probably look much brighter than they would if you were able to look at them directly.
That's cool. Darker than asphalt. That's
Yeah.
very dark.
And Osiris-Rex doesn't have a light source, so it's using the sun, and then it can measure the height based on the shadows cast in these images. And this is a mosaic that they assembled of the Nightingale site, and you can see some of the things. But yeah, like he's saying, it's not so much probably very accurate as terms of color, but the lightness and the shadows, the contrast is resulting from the sun, and when they record the images.
And how many years do we have to wait for this to come back?
This is coming back in 2023, so not that long from now. I mean,
No.
it's right around the corner from somebody who has to worry about getting ready for it.
True.
So
yeah, right now, do you guys happen to know like where Bennu is with respect to Earth's orbit around the sun? Are we on the same side together right now?
I'm not exactly sure where the orbit is specifically right now. I think it's definitely a near Earth asteroid, so it probably crosses our orbit frequently, but I don't know exactly where it is.
That's fair. I'm just a weird spatial person.
Yeah.
I sometimes
Yeah.
need to know.
I do think if you're on Instagram, there are some really cool Osiris-Rex filters, and one of them has Spacecraft and Bennu, and you can kind of circle around, so they've got some fun if you're an Instagram person.
That's awesome.
So that doesn't necessarily help you with spatial awareness, but it does.
Das is helping.
I'm
right
on
now.
it.
Oh, there we go.
There you go.
I can't read that, but you tell me what it says.
So we've got, it's almost on the opposite side. I've got 101955 Bennu, which is the correct Bennu, right?
Yes.
And Earth is not quite 180 degrees around this other side of the solar system right now. I think I got this set to the current date. Yeah, September 17, 2020. So there is Bennu, and then Earth is over here. And you can actually see Mars 2020 that just launched is leaving Earth over there on its way to Mars, but Bennu's all the way over here.
Thank you, Das.
From our previous Virtual Astronomy Live, where we learned about NASA eyes. This is what I brought up on the screen. Ta-da!
That's awesome.
Tying it all together.
Hang on a second.
There you go.
And tell me what Osiris-Rex actually stands for. Is it a backronym, so to speak?
Yes, and I'm so bad at remembering this. So it's an acronym that the team put together basically to highlight all the different goals of our mission, right? And so it's origins, the O, for, where we come from. It's, and I remember Dante telling me there's be a quiz, and I didn't write it down. Spectral imaging, the SI, right? Because we're taking pictures. I can't remember the R, but I'm failing my quiz. There you go.
There you go.
Das to the rescue.
Resource identification, security, and then the regolith explorer. And so these are kind of an encompassing of all the different goals that our mission had, and they made this really cool acronym about it.
Yeah,
and it also kind of ties to the Egyptian god Osiris, because of the sun and looking forward, and we're looking forward here. And So it's pretty cool.
And Bennu being maybe an Egyptian bird.
Yes.
So that's very neat, nicely tied together.
So yes.
How soon do the maneuvers start for this actual, the touchdown?
We've
Like you say,
already
it's going to happen on the 20th, but what's happening between now and the 20th? I guess
so between now and the 20th, we've already started, the team's already started getting, the daily codes, making sure, because, we have to make sure that the spacecraft comes out of orbit and is in the right position. And all of these things are small maneuvers, right? So they take time. And so it takes a long time to get it all lined up exactly right. And so the team is already planning on when a lot of these codes and these signals get sent out, and how they're going to interpret them. And we've already been through this practice now twice, so this is kind of the real deal, right? Third time's the charm. And so it's so it's already starting now. We're already starting to get things ready and plan and getting the spacecraft oriented exactly right. And so yeah, so it's only 5 weeks, which is not a very long time.
Right.
So we're very excited though.
Is there going to be a live broadcast?
So yes, and I'm not sure exactly how that's going to look. I know if you watch a lot of the social media and the NASA site and the asteroid mission site, they'll have more about it. We're trying to evolve it. The original plan is this giant press event. We're all going to be there. Well, now we can't all be there because it's not safe. And so I know they're working on how they're going to end up showing that type of press event, but I know there's going to be a big thing that's going to be out there. So it's going to be really cool.
Yeah, I will definitely stay up if I have to, or wake up early, depending on.
Exactly, because all these different time zones across, Europe, and then because of the D-Space network, and then through the United States.
Yeah.
But if you keep watching, we'll post stuff up on it. Really active Twitter account as well. If you're into Twitter, they do a really cool job with it.
They do. That's where I follow them the most.
Yes. And if you love puns and Valentine's Day, their Valentine's posters going back, top notch. The puns and the Valentine, I love them. I don't know if you ever saw those, Christopher, but they're phenomenal.
No, I haven't.
I love present day NASA. I mean, I love NASA always, but there's so many amazing social media things, and they're really getting hip with the kids, and they're doing a great job.
They really are. And just how, yep, there you go. Oh wait, their galleries. Yep, there you go. You gotta love it.
That's great.
Those are amazing. And that's probably, that just reminds me of your poster behind you, Chris, because you have the...
Oh, right, the Mars poster, yes. And another interesting thing, I don't know if they're going to do this for Hayabusa 2, but I know for the first Hayabusa mission, JAXA made trading cards for all the particles that they analyzed, which was really cool.
Wow.
So I love outreach sort of things like that.
Yeah. And remind me when the Hayabusa 2 is coming back before the end of 2020, right?
That's coming back in December, and that's going to be really exciting because it's going to be a much smaller sample, but it's going to be the first such sample. And the plan was for me to and the Hayabusa 2 curator here, Keiko Nakamura, to go to JAXA when the sample canister is opened and everything. But with travel restrictions, we'll see. We'll see how that all works out. But it's going to be really exciting because it will be the first carbonaceous asteroid sample. And from our perspective, we're going to learn a lot about how to get ready for Osiris-Rex based on their experience. So it's really been fortuitous that these two missions are flying at a time so close to one another. We found that the shapes were very similar. We found they both had these surprisingly rocky surfaces, and just a lot of interesting things to do these at the same time.
And were you part of the Hayabusa team that was working on how to retrieve that sample?
No, I collaborated with JAXA on sort of particle handling techniques, but I have not been a participant in the design of collection mechanisms or anything like that. which would have been fun, but I was still in graduate school at the time, so.
Oh, fair enough. Fair enough.
So.
Yeah, that's really cool. It's like a teaser, or like, a rehearsal, dress rehearsal.
And they're going to be both very interesting samples in their own right. JAXA is actually going to try to do a gas sample analysis of their sample. We'll see how that works, but there's going to be a lot we're going to learn about these bodies. And talking about the TAGSAM, if this works really well, and we're all hoping that it does, this is going to be an amazing new way to collect samples from all kinds of bodies. You can use something like this to collect samples from comets. You can use this for all sorts of other bodies to see like what the heterogeneity is in the asteroid belt. So it's going to be an exciting thing. And we're doing all sort, sample return is something that we hadn't done a lot of between, say, the end of the Apollo era and 2004, 2000 or so, because we basically, I don't know, we just didn't do it. And then we had missions to collect solar wind particles with Genesis. We had Stardust, which collected comet dust. JAXA's doing sample return. We want to go back to the moon and get more samples with Artemis and maybe bring back some ice. JAXA is going to a Martian moon with the Martian Moon Explorer. And then we've got, Osiris-Rex and Hayabusa 2. And then we've got Mars 2020 caching samples for Mars sample return. So this is a really, really exciting time for sample return and for Astro Materials curation, because the best place to study these samples is back on Earth, where we have the best instruments. You don't have to miniaturize an analytical instrument or a mass spectrometer to figure out what you have, and then people can repeat the experiments. So it's really a golden age for sample return.
Yeah, and like you're sitting right in the middle of it.
Yeah, it's exciting.
That's awesome. So we are kind of running up against time for this free talking portion, but As has a whole bunch of questions from people on the Twitch stream, so I'm going to hand it over to him.
I do. While we've been sort of listening into the fascinating discussion and me frantically digging through the 100 images I have, trying to display the relevant one, people have been asking questions. Folks, as we go through this, you can still ask us questions. If you have a question, just start it with the word question, and we've got some software on this end that'll pull it out and put it into a little queue for us so that we can go through and do some Q&A. But are we ready to go with that?
Yeah.
All right, cool. So I'm just going to jump right in after I click on the correct thing here. There we go. All right. So I'm just going to jump right in with some of the questions here, starting off with one from Squish, who asked, when maneuvering the spacecraft to the target location, how's the rotation of the asteroid factored in? So is the gravity low enough that it's more like station keeping? Is the spacecraft flying around and it has to correct itself? Is the orbit at the exact right, I guess, orbital period that you're sort of Bennu stationary over one spot, or how do y'all account for that? That's a great question.
That is a really good question. You want me to do it, Chris? You want to do it?
Yeah, I actually don't know. So
I can't help, so.
Oh, there you go. Sorry, so I'm not going to be as technical as one of the programmers would be. Basically, we know how the microgravity around Bennu. So Bennu has its own little microgravity, kind of like how Earth has gravity, right? So, and the moon has gravity. Everything has its own little gravity. And so Bennu's microgravity is taken into account when we do the calculations on how we maneuver the spacecraft down. So we are taking the rotation into account, and we are taking the microgravity into account so that we can land precisely down on its spot. Similar to how some of the launches have gone up into space and come right back down, right? So we know the orbits of Bennu, we know its speed, we know its orientation, and we know its gravity. And so we're able to use all of that to calculate exactly how we maneuver down, how we orient the spacecraft, at what angles we need to have everything so we can come straight down.
And I've actually got a really cool visualization. I didn't know that it did this, but in NASA Eyes, they actually have the rotation of Bennu and the orbit of Osiris-Rex I don't know if this is exact, like, is this sort of a representation of it? But check this out. The reasons it's sort of complex is because Bennu is spinning like that. I don't know if that's the exact spin of Bennu, but that's what we're seeing in NASA eyes here. And then Osiris-Rex is orbiting it and going around it. And so if you want to hit a specific parking spot sized part of the surface, you have to take all this motion into account. Again, this is what I'm getting from NASA eyes, and it's sort of illustrating those two things, but I don't know if this is exactly the exact rotation of the two. But that's why it's so complicated. I love that parking space analogy, the little graphic that we had that showed how small it was. Because a lot of people, you look at this stuff and you're like, wow, I don't know. It's a spacecraft. It's out there. What is it, like the size of an RC car? Is it the size of like a bus? How big is it? And getting it down to, wow, I've got to park my spacecraft with its little sample arm in a parking space on an asteroid on the other side of the solar system that we can't communicate. We have to program all this. It's crazy that even works that way.
It is. And, also, I mean, you can see here in some of the images, Bennu is not circular. It has a definite, shape. It has an equator. I mean, it's a very obvious not circle.
Yeah.
And so its orbit is also a bit elliptical around it, kind of, so it's very well illustrated here. But you can see, so you have, it's not like you just have this perfect circle and you're going in a perfect circle. You have this odd shaped body that you're orbiting around in this elliptical type orbit, and you have to get closer and closer, and as you get closer and closer and spinning through, you have to take into account the microgravity will increase, and it will and so there's a lot of physics involved in all of that to figure out exactly where we're going to go. And then on top of that calculation, the spacecraft then has to watch for rocks, and so it uses its little brain, this natural feature tracking that's stored in the spacecraft, and it kind of says, okay, yep, I'm lined up exactly where I need to be, and I'm just going to keep coming down. I'm still lined up, and it's just highly impressive.
It's like, imagine, the cars these days, and it's like, oh, my car can park itself in the parking space because it's got cameras or sensors or LIDAR or whatever. The spacecraft launched how long ago, and it's parking itself in a parking spot on the asteroid? I think that's, when I say parking, remember, it's not landing, y'all. It's not going to sit there and stay. It's just got to target that small spot, right?
The fist bump, as we were calling it, right?
The fist bump. I like that. God,
and the sample head is about a foot in diameter. It's like a 12-inch, circle. So you've got that on top of your spacecraft on this arm that I think is like 11 feet long. So, I mean, it's, to give you some perspective there.
Yeah, I think I've got, that looks like an older visualization, but here is the arm actually deployed, right? Let's see. That would be this one. And so that arm is 10, 11 feet long, and that's a pizza on the bottom of it. I say a pizza, 12 inches.
Yeah, it's about yay big.
About yay big. I like it.
About 18 inches, 24 inches, something along those lines.
Oh, I apologize. I thought it was a foot. Yeah, it's a little bit bigger than that.
That's it's so cool that with a degree of accuracy, because you also don't want to crush the arm. You don't want to come at it too fast so that you impact it and the arm gets bent or something. I mean, all the different things that have to happen, not only correctly, but autonomously. The spacecraft just has to do it right, And I love the illustration where you showed it sort of waving off. I don't know if I can find that again, but...
the natural feature tracking description has it.
That has an N. It starts with an N, so that's what I'm going to look for. Natural feature tracking description. There you go. And this was the one we were sort of looking at. It's using its cameras and it's using its sensors to look at the terrain below it. And as it gets close, if it's going to crash into the boulder that it doesn't want to, not crash into, it doesn't want to land there. It wants to land where the dot is. It'll wave off. And that's not a person hitting a button, right? That's not, oh, mission control, oh, quick, hit the button, and, in the movies or whatever. This is the spacecraft doing it and then telling you about it later.
Yeah.
All
that's
right.
Exactly right.
Lots of good questions, so I'm going to keep going through them. Here's one, in Christopher, this one might be for you. What tools or methods is NASA using for particle composition analysis? So.
Oh, yes. We use a lot of different tools to understand the compositions of particles that we use for meteorites. We use it for cosmic dust, and so these are pretty well-established techniques. The one that a lot of people use to understand the mineralogy, they use a transmission electron microscope, a TEM, and that involves taking a sample and making a very thin slice of it, like usually only 70 nanometers thick, and shining electrons through it and understanding the crystal structure, and you can get the chemistry and the crystal structure and understand what minerals you have. You can also use things like ion probes, mass spectrometers that ablate a little bit of the material away, turn it into a plume of ionized particles, and then feed it through a mass spectrometer. And this will allow you to understand what elements you have there and what isotopes of elements you have there.
Like,
so the isotopes are actually very important. I specifically also care a lot about things like oxygen isotopes, because that tells you a lot about the environment in which they form. It's like this really great forensics of how the solar system formed and what were the conditions 4.5 billion years ago. And so we use those things. We use scanning electron microscopes. We use all sorts. Some of the times we even use synchrotrons, X-ray beams, and large synchrotron facilities to understand the crystal structure of these things. So this is the great thing about sample return. You can't fly a synchrotron to Mars and analyze a sample.
It sounds like a synchrotron is a big thing. You have to have a building to put a synchrotron in, not a spacecraft, right?
Yes, these are huge. These are huge facilities.
Gotcha. And
so those are just a few of them.
Clarify a couple things. Like you say, oh, you take a slice that's 74 nanometers thick. Like, what does that mean? I don't. 74 nanometers. That sounds small. It's got nano in it, right? Those nano SIM cards you put in your phone, they're small. So nanometers must be small.
Yeah.
If I had a piece of glass or something that was 74 nanometers thick, could I hold it? Like, how small is that? I don't even have a concept.
We have them on. We hold them on these grids that they're basically thin films. They look like thin films. When you slice them, they come off, and you can tell how thick they are by how they reflect light. But to give you context, people's hair is usually about 50 to 100 microns thick.
Microns.
Right? 1 micron is 1,000 nanometers. So when you're talking about a slice of 70 nanometers, you're talking about, a very small fraction of a micron. So these are incredibly small and thin things, but this is a technique that's been used for over 50 years, maybe closer to 100 years, making these thin sections of samples to look at them with an electron microscope.
I mean, I don't even understand the technology that would allow us to slice something that's like 1,100. It's like a lot smaller than a hair, right?
It's funny because it's not a very complicated instrument. There's a device we use called an ultramicrotome.
Okay.
It's basically a stereo microscope and an arm that mechanically advances forward using thermal expansion. And so it's a pretty old-ish. I say old. I mean, it's not advanced AI technology. I mean, this is a mechanical thing.
You just said an arm that advances forward through thermal expansion? So you have an arm and you heat it up, and the fact that it got warmer made it get a little bit longer?
There's a large ballast in it, and I think I don't exactly know how it works, but it is advancing forward in these steps by thermal expansion, very reliable thermal expansion, which is pretty fascinating. And then we also have all sorts of other more sophisticated devices to embed these particles in epoxy or sometimes in molten sulfur. So these are a lot of techniques that have been used for decades and a lot of techniques that we're coming up with right now.
It sounds like a good time. Molten sulfur and arms that expand through thermal expansion. So you made a comment about you were taking a sample, you were sort of ablating something off. What does that mean? Like if I'm ablating something, am I scratching it? Am I blowing on it? Like if I need to get a sample by ablating it, what does that mean?
So in an ion probe, what you'll do is you have a sample that you've polished flat, and you have it in a vacuum, and it's being bombarded by a beam of ions, a cesium beam or an oxygen beam or something like that. And those erode the sample and make the small crater, it's like only 10 microns big, and this crater ejects this plume of atoms. Some of them are ionized, some of them are neutral, and in terms of the ionized species, those get accelerated through a number of magnetic and electric field lenses, and they are transmitted through this device. And because you have this big magnet and you have everything with the same charge, heavier things bend differently through the magnet than lighter things. So it's just like light,
right?
You know, you have red and blue and green light bending at different angles. These different masses bend through the magnet in the same way, and they're counted on these cups. And that's how that is done. And then you can figure out the ratios of these things.
Right. I mean, you use the term electric lens. I mean, I know what a regular lens, like a magnifying glass lens is. It bends the light.
Yeah.
I assume this is some sort of electromagnetic
Yeah.
field that bends.
When I say things like electric and magnetic lenses, we call them lenses, but they're basically manipulating beams of charged particles in a way that's analogous to how a lens of glass would manipulate things. I don't know how far you can take that analogy, but it's a convenient terminology that we use to shape things.
We'll go with it, and if we get it wrong, just blame me. It's like, well, Das was trying to understand an electric lens, and so he just sort of said. But the thing about this is people need to realize when these samples come back, this isn't like Christopher here with the magnifying glass, like, oh, yes, this is very interesting. It's not a visual, putting it under the microscope sort of thing. There's a lot more than just having a look at these samples to figure out what they are.
Yeah, there's the worldwide team of scientists who are going to be participating in something called preliminary examination.
Yep.
Where the people who proposed the mission, the principal investigator, Dante Loretta, and a team of people who have been with this mission since the beginning will sort of have a first look to ask some very fundamental questions that we want to know. And after that period is over, then any researcher in the world who wants to do research on these samples can apply for a sample, and it goes through a review committee, and then they get allocated a sample.
Can I fill out a form for that? Can I be like, oh, yes, I would like to hold a sample really close to the camera on the live stream? Would you think that would get approved? Probably not.
It's a little harder to get a sample than that.
Well, I could try. Let's get some more questions here.
Yeah, sure.
And I've got, let's see. This is actually a really good one because we were talking about planetary protection and trying to keep the samples pristine. But our intro here asked, scientists talk a lot about the, and they put quotes, pristine material that's been thought to be floating around in space, being irradiated, impacted for 4.5 GYA. That's probably just a long time. For those who don't get it, how can anything that old that's basically floating around in space, getting irradiated and bombarded, how is that pristine? Like, what do we mean when we say a pristine sample? That's a good question.
Well, yeah, there's a lot of argument about that term, pristine, and we also like to use primordial and primitive. But there is a lot of argument about how much alteration has occurred with these samples from the beginning of the solar system. So first and foremost, you can only work with what you have, right? And in that sense, meteorites go through a lot of alteration on the parent planet, on the parent body,
right?
In terms of impact and radiation. It gets ejected from the body and eventually goes into an Earth-crossing orbit. It ablates through the atmosphere. It gets oxidized, depending on whether you pick it up right away or whether it's been sitting on a surface for thousands of years.
Yep.
There's terrestrial weathering. And yet you can still find interesting things out about the formation of the solar system through these rocks, because Earth rocks, unlike meteorites, have all been sort of recycled through this process of convection. There's no original, these are the rocks that formed the Earth on the Earth. Everything that we get that we know that predates or goes back to the formation of the Earth comes from meteorites. Now, that being said, if you want to start looking at more pristine things, you can start collecting them on the parent bodies. Comets are especially interesting because we think they've always been kept cold like far away from the sun in the Kuiper belt, and their orbits have been only relatively recently perturbed. And so when we get comet samples, we think that those might be even more pristine. And we see things in them in these samples, like pre-solar grains, for instance. We think that most of the material in the solar system was homogenized in the condensing of the molecular cloud, and then you have this solar nebula, and there's this hot, intense gas, and everything's vaporized, and things start to condense out of this gas of solar composition. But some things survive that, and we understand that through their isotopes. They have isotope compositions which can only be explained by formation in the atmospheres or the cores of a star.
Gotcha.
And so there are things, there are clues, but yes, people argue about this. There's a Lunar and Planetary Science Conference every year, and people argue about these things all week long. So
I almost wonder if the person who posted the question attends those conferences or not.
maybe.
But so, to circle that back, I think it's pristine. It's something that hasn't been subjected to like Earth's atmosphere or erosion, rain, that sort of stuff. Because even if you find a meteorite on Earth, it's likely that that has been subject to the geological processes or the weather processes on Earth, and so that's been changed. It may have picked up other things once it got here on Earth. And so I think you mentioned this during our pre-call. It's almost like we've given this sample its own little spacecraft to protect it from the atmosphere and the exposure and that stuff as it comes back down again, right?
Yeah, it has
Exactly.
a bubble that protects it as it comes through. So we'll see what it looks like taken directly from the surface. So pristine, yeah, like you're saying, pristine in the sense that it's not been through all the contamination of Earth, but it's seen all the contamination that the surface of Bennu has seen.
Yep.
And that includes, impacts from other bodies. It includes irradiation from the sun, and maybe galactic cosmic rays. There are all sorts of effects that these things see.
Yep.
And we try to deconvolve all of those.
Yeah.
But that's like you were saying, you can only use what you have, right? So
Right.
until we invent
Exactly.
a NASA time machine, I think that comes in after the EM drive, right? We have EM drive, and then we have go to time machines. But until
Something
you get
like
that, and you
that.
go back 4.5 billion years or whatever, we can only sample what is out there in the solar system that we can get our hands, our manipulators, our stainless steel contact pad
Yes.
or whatever we can get our hands
Yes.
on. We'll just leave it that way. Let's grab some more questions, because this is what we tend to do. Like, I get one question, then I get so interested in all the different things about the question, and we talk about it for 10 minutes. We always run out of time for the Q&A. So let's see here. Here's one from Raven McCoy, and they asked, what is the coolest thing you've learned from an asteroid sample? So both of you, Salwa, you start, and then we'll go to Dr. Christopher. What's the coolest thing you've seen or learned from a sample?
So I don't have a lot of experience with this because I'm relatively new to NASA in general, but yeah, I don't know. I'm excited to see. I know we're thinking that there might be some water-bearing clay materials, so I'm excited to see that. But Christopher is our expert on samples and space rocks and things, so he's going to have a really cool answer.
Well, I think one of the coolest things that have been learned from meteorites is the age of the Earth. So that was a really big and amazing thing to learn. I think also, I'm kind of biased because I did my PhD research on this, but I find that the oxygen isotope compositions of these meteorites and how they cluster and clump and how they point to a solar origin and then an origin of some other composition tells a very interesting story about how these materials came together in the formation of the solar system. I think every time you put one of these rocks in an ion probe and you get the data off of it, it just looks like numbers, but you could just be seeing something that's never been seen before. And that's always that's kind of a rush for me.
Nice. It's like the Matrix, right? Where you have the operator and they're looking at the lines of code and they're like, oh, all I see is this, that, the other. It's the same thing. You see numbers that come back, but it means something to you.
But there have been so many cool things that have been learned from meteorites, like the organic compositions of these things and the complex molecules that you find in these meteorites. the evidence of aqueous alteration, understanding how much water was present in these samples.
I was going to guess that meant water because it said aqua at the beginning. So
yeah, so that's one of the interesting things about both of these samples, especially Ryugu, is that we think there's going to be a lot of hydrated minerals on there. And there's always this question of where did the water on the Earth come from? And whether asteroids and comets could have been part of that delivery process, or whether the water was something that was present in the original bodies that accreted the Earth. This is an ongoing debate. I think that's a very exciting prospect. And also, how many generations of planetesimals were there before you got to a Ryugu and a Bennu? Ryugu and Bennu are probably not primary planetesimals that originally accreted. These are things that probably are rubble piles of previous generations of things. And so that's going to be a really exciting thing to understand.
So it's like they formed after the solar system formed. Like the solar system formed, and these planets formed, and these things formed, and then things broke back apart, and then recame together some number of times to form Bennu, right?
And the timing of that is very interesting. And it's also interesting because we can now do astronomical observations of other solar systems that are forming around other stars, and sort of compare the information we get from the radio astronomy and the infrared astronomy from those things with what we see in meteorites. So there's this convergence of astronomy and meteoritics to tell the story of not just how our solar system formed, how do solar systems form in general?
Yep.
And that's just super exciting.
I like that. I can correct myself because I said, oh, we don't have a time machine, but we kind of do have a time machine.
Yeah.
If we look outside our solar system, because it takes the light of all the stars, everything around us, time to reach us, we can see, I guess, planetary systems, star systems in various stages of formation, right?
Exactly.
Depending on how far away they are. That's our time machine.
Yeah.
I like it. Let me grab a couple more questions here. This is a good one, and I can sort of start with this one. The question was, how did they know Bennu was going to have its own gravitational influence? And how did they know that they would be able to stay in orbit? So we can sort of start that because we figure Bennu was probably made of mass, and things that have mass have gravity. They have gravitational attraction, right? But how did we know how much mass it had? How was it going to affect the spacecraft? Like, how do we know that we would actually be able to orbit it, right? Because it's challenging to orbit, right? Solway, did you?
So that's a really good question. I'm not sure I'm even qualified to answer that, but
neither.
I can try.
Well,
Christopher?
I was going to say, in general, you can know the mass of an object based on its orbital characteristics. You can also know things about its inertia, its moment of inertia, based on orbital things. And so you can begin to get things like porosity of a sample. And I think we kind of suspected that Bennu and Ryugu were somewhat porous. And so you can design a spacecraft to operate within a range of those masses and porosities to orbit it. And, you know, we haven't brought back a lot of samples from other bodies, but we've sent spacecraft to lots of different asteroids and comets. You know, there's a whole list of things that we've actually visited. And so we have a little bit of experience understanding how spacecraft interact with these bodies.
Right. I mean, I know that's one of the. We won't go.
Sorry.
Go ahead.
I was gonna say, and every planet, every space body does have its own form of its own gravity field, its own gravitational field. And you can sometimes see that through other, like we have our moon, other satellites, orbits, things of that, how the comets pass them. So you can use some of those trajectories and things too to try to help with understanding that.
Yeah, absolutely. We've orbited a couple things in our time, right? And then it sort of comes down to mass. I mean, I think Bennu is really interesting because when you start doing the math, it's like, imagine a perfect sphere of mass whatever, and that's the easy equation. And then you get it into, imagine a lumpy sphere that's got like this much mass over here, then it's kind of porous and it's kind of dense over here, but then there's a big boulder that may affect you. And how do you get from your easy equation to there's a real rock out there that's a big bunch of lumpy stuff that we need to stay in orbit around? Because it does have gravity. Go ahead.
Yeah, I was going to say, I'm always in awe that we send spacecraft to bodies and land them and pick things up. I mean, I know it's science and it's math, but it still is just amazing when you think about the distances involved that we can do this so well. It's just, I am always in awe when any of these things work.
Yeah.
You know?
I like it because again, it's not somebody there with a joystick. There's not somebody in mission control hitting the big red button like, oh no, we have to save the mission. By the time it goes there, you've either programmed it and built it correctly and tested it enough and simulated it as much as you can. It's gonna work or it's not gonna work. Like it's out of your hands.
And I'm also always amazed at the fact that there was some person somewhere, some group of people in a machine shop who cut metal and assembled things that were designed, and that metal that this person or these people designed is now rolling around on Mars or flying around Bennu or Ryugu. I mean, to think about that, I mean, that's really just an incredible thing to me.
And the power sources and the wiring and having to protect all of that from the space radiation and other, I mean, it's such a harsh environment. I have problems getting my laptop to work sometimes,
Exactly, right?
Batteries and, all of this equipment that has to go out there and travel through all these different environments out there, plus getting launched. I mean, that's not an easy environment either.
I mean, the rocket launch itself is like it's not a floaty feather just going into space. The launch itself that it has to make it through is a harsh environment for the spacecraft. So, as always, we always get to the end of this and we always run out of time. I still have more questions in the queue, but we are out of time for our live Q&A. There were some really quick things I wanted to ask, and I think it may be almost premature to ask here. Would we change Osiris-Rex any? If we wanted to have, let's order 3 more and send them to other targets. Have y'all come across anything that we could improve on what we've learned so far? A little difficult before we actually get the sample back, right? But any comments on your next generation asteroid sample return?
I don't think so. I mean, I'm not one to say too much. All the concerns we had about how everything was going to operate have just performed flawlessly. There was some concern about, are we going to have enough light? And obviously we do from the sun. And, so I think it was designed very efficiently and just robustly that it's made it out there. It even was able to take images of the Earth as it was traveling out, that we hadn't really even planned for, and phenomenal images and stuff. So I've been very impressed with the design and the team and the construction of it. Like Christopher was saying, I mean, just phenomenal. So I don't think of anything right now that we would change.
I do remember there was a conference in November about asteroid science and the age of Osiris-Rex and Hayabusa 2. And this question was asked to the PI, Dante Loretta.
Yeah.
And I think that he said that he really liked the technique of using target markers that Hayabusa 2 used. And if he did it again, he'd probably have some kind of target markers on it. But, maybe he'll change his mind when it actually touches down perfectly in that little bullseye.
Yeah, so, the little bullseye. Gosh. Well, thank you all so much. Let's bring Summer back in here really quickly. Like this. Summer, we got you back?
I think so.
Alrighty. So again, like I say, we always run out of time for these events. We have so much cool science that we can share, and I have all sorts of crazy questions like, what is an electric lens? How does that work? But I really do appreciate y'all joining us here today. Again, our moderator, Summer Ash. Summer, thank you so much for the time.
My pleasure.
All right.
I also agree with Christopher that the fact that we can do any of this is amazing.
Absolutely. Especially they go out there and they're sort of our children off in the system doing our bidding. I don't know if that's the right way to say it, but you know what I mean.
They really do start to feel like your kids or your baby. They're out there floating, and you're proud when they do the things they're supposed to do.
Yeah, absolutely. Solway Irvine with NASA Marshall. Solway, thank you so much for the time today.
Thank you for inviting me to this. This was phenomenal. I really appreciate it. Thank you.
Excellent. And Dr. Christopher Sneed with NASA over at Johnson as well, right?
Yes. Thank you. This was great. This was a lot of fun.
Good deal. It really was. Thank y'all all for the time. Remember, y'all, we're able to do these events. The live streams don't just magically make themselves happen. Intrepid Museum's Virtual Astronomy Live is supported through the NASA Cooperative Agreement that was awarded out by the New York Space Grant Consortium. So thank you, New York Space Grant, for helping support these streams. We've been doing them just about every month ever since we've been sort of locked down, and they really are fantastic ways to get some more cool information, share how cool we think all this stuff is with people that are literally all over the world. Speaking of that, our next show coming up next month is going to be concerning food in space. And I'm not going to read the fine print there because it says something about shrimp cocktail that they're sending to the space station or something. I'm not sure that I would probably pass on the shrimp cocktail, but that is going to be next month, October 15th, same time, same channel, coming up for our next Virtual Astronomy Live. But for this evening, that is going to be the end of the show. Again, thank y'all so much for joining us, and we will see y'all next time. Everybody, thank y'all for joining us. I feel like I should do the Brady Bunch thing, like looking around. But thank y'all for the time here. One more time, we really appreciate you taking time out of your day and sharing some cool asteroid stuff with us.
Thank
All right.
you.
Thank you.
We will see y'all next time, folks.